All right, so let us now continue our discussion. Okay, so can you guys see my screen now?
Yes, sir.
Yes,
Yes, sir.
sir.
All right, so this is where we've stopped last meeting, right? Can you guys still recall, or you guys already forgot? Where did we stop last meeting?
Yeah, we stopped. I think.
Power
Yeah.
at
Yes, 5 HP.
All right, so Mr. Follower was really paying attention, so very good for you. Okay, all right, so I guess we were able to finish this one, right?
Yes, we did.
All right. So again, if you want to convert the watt into kilowatt hour, okay, so you have to divide it by 746. All right. So this is your question last meeting, Mr. Palawewa. All right. So let us now proceed to the example number 6. So it says here, what is the resistance of a load that takes 2,500 watts from a 115 volt source? Okay. Well, anyway, this is just to show that you can solve R using the power and voltage source. So you can see right here we have a given voltage source of 115, and then the another one is power, which is 2,500 watts. So just substitute it in here. So using this formula, so E squared, so 115 squared divided by 2,500. Okay, so just put this in your calculator, then you will get this answer. Right? So can you guys verify whether this one is correct or no?
Tama, sir.
Tama. All right. Okay, so let us now move with electric energy. Okay, so since power is the time rate of doing work, okay, sometimes stated as the rate of expenditure of energy. Okay, so you could say that when you say energy, you could also say that it's equal to power. Okay, there is power, there is energy. There is energy, there is power. Okay, so it should be clear that electric energy is the product of power, watts, and time. So you can also do this one with power, wherein power is the product of electric energy and time. Okay, so I drop those two. So assuming constant electrical quantities during a period t seconds. Okay, so in here we now have a time wherein t here is in a second. Okay, so initially we have this formula. So electric energy is equal to power. And then this power has a formula of EI. P is equal to EI. So just substitute it right here. Then you can now form this new formula. And then again, you can substitute the value of E to I squared, or IR rather. Okay, so forming an I squared times R. Okay, so nothing has changed with our T. Our T is still right here. So for consistency, let me just make this one small t. Okay, and we have here another formula wherein just by substituting the I into V divided by R, or E divided by R, then you will get this formula, E squared divided by R times T. Okay, so we could say that this one is equation number 14. All right, so all I need to do is memorize this one. Well, actually, this one is quite similar with energy or power. It's just that there's an additional T, or the time. Right? Okay, so moving on. So note that a joule is equal to watt second, where P is given in watts and P is in seconds. Okay, so before we have 1 watt is equal to 1 second, right? It's right here. So since the watt is equal to second, or watt to second is ordinarily too small for a practical computations, a larger unit, the kilowatt hour, is generally used. Okay, so that is actually what we are using in terms of our everyday usage here in our home. Okay, so they measure our electricity usage electricity consumption rather, via kilowatt hour. Okay, so we have this formula when it comes to kilowatt per hour. So P is the power times the hour divided by 1000. Okay, so let's have an example using this formula. We have here the example number 7. So how much electric energy in kilowatt hours is delivered to an electric motor during an 8-hour period when operating from a constant 230 volt source? Okay, so if the average currents are 34 amp for 2 hour, and then 38 amp for 1.5 hour, then 26 amp for 4 hour, and then 12 amp for 1.5 hour, 1/2 hour. Okay, so just let's just imagine that those currents are different loadings or different appliances. So we have here 34 amps for 2 hours. So maybe let's say that's an electric fan. And then we have another 38 amps, which has been consumed for 1.5 hour. Say that one is a television. And then another two appliances. Okay, so if you're going to add all of those, 1/2 hour, 1.5 hour, 2 hour, and then 4 hours, you'll get the 8-hour period operating at a constant of 230 volt source. Okay, so the question here is how much electric energy in kilowatt hour is delivered in our electric motor? So just get the formula. Okay, we have here the EIT. So E is for the voltage source, and then I is for the current, and then T is for the time. Okay, so as you guys can see right here, we have 230 for the voltage source multiplied by the current, which is this one, let's say the first appliance. And it was consuming the 34 amps for 2 hours. Okay, so this one is already one energy. But we still have 4 more appliances. I mean, 3 more, rather. So here's the second one, here's the third one, and then the fourth one. So as you guys can see, the only difference is the current that is being used, and then the time that is being used also. Okay, so just do the math, okay, all of those, and divide it by 1000 since it is asking us to have a kilowatt hours. Because if you're not going to divide this one by 1000, you will get watts only. Okay, wherein you have to divide it by 1000 for you to get the kilowatt hour. Okay, so just do the math, okay, or using your calculator, input this one, and then you will get this answer, 54.05 kilowatt hour.
Excuse me, sir.
Yes.
So I want to ask, why do we have after the old power, after the old energy calculation, that we have multiply by 1 before dividing by 1000? Why do you have the multiply by 1 again?
This one. Yeah, why
Yeah.
do I have this one?
Yeah.
So supposedly this one is in a form of
Oh, that's 1 over
like
1000.
yeah, 1
Okay.
over 1000, something like that.
Okay. Thank you, sir.
So so you can just remove this one and then divide it by 1000. So the whole equation itself. So let me just pick this up, since this one is quite confusing. Okay, 1 divided by 1000. There you go. All right. So any other concerns so far or clarifications? So is everything clear for
Yes, sir.
now?
Yes, sir.
All right. So let me give you guys your first assignment. So supposedly, give this one to you as your assignment, but we wasn't able to reach this part. So example number 8 will be your assignment number 1. So a water heater has a resistance of 5.3 ohms and takes 43.5 amp when in operation. So as you guys can see, super easy. Only one appliance. So if it is in service on the average of 2 hours per day, how many kilowatt hours of energy will be expended during a 30-day month? Okay, so I guess this is just the only additional one, okay, from your last example. So I would like you guys to calculate for the kilowatt hours of energy that is being delivered by this water heater. Okay, so you can answer this one in a Microsoft Word. Okay, so here's the thing. If you can answer this one in the Microsoft Word better, okay, so just use the Times New Roman or the Corriero or any font that is easy to read, okay? Or you can use Century Gothic, which is the one that I'm using, okay? Century Gothic, okay? But if you cannot do this one on Microsoft Word, wherein like you're not really familiar when it comes to putting equations, so you can do this one handwritten. However, please write legibly, okay? Because if I cannot understand your solution or your handwritten, then you might get a 0, even though you've got the correct answer. Okay, so please write legibly. Okay, and not just write legibly. Upon taking the picture, let's say you have your camera right, must have a proper lighting. Okay, so it must be bright enough for me to easily see it. Okay, so as you guys can see, there's a lot of issues when it comes to handwritten. Okay, so there's a lot of a lot of factors wherein it will affect the quality of the the cleanliness, the neatliness, etc., etc., and other factors that it will affect the your handwritten. Right. So are we clear so far regarding with your assignment number 1?
Yes, sir.
How about the others? Can you guys still follow?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Yes, sir.
Kala ko nag-ML na kayo eh.
Yes, sir.
Anyway, okay, so let us now move on to heat energy. Okay, so current through a resistor always involves a conversion of electric energy into heat energy. Okay, so that is one disadvantage of using a resistor. Yes, it is limiting the current, but at the same time, it can also affect the performance if the heatness of that resistor is like it's overloading already. Okay, like it can melt the component itself already, especially if it cannot handle the high current that is passing through on that resistor. Right? It's really super hot. So have you guys touched a resistor before, wherein like it's working, a circuit that is working, okay, under electricity? Have you guys touched it after that one is under the work of electricity?
Hot, sir.
Yeah. So to those who have experience in touching it, so it's really hot. Okay. So in most scenario, okay, the heatness that is flowing onto our resistor will depreciate or will not be able to perform. Like for example, he's performing 100% for 5 minutes, but upon reaching 30 minutes wherein it's already super hot, it's slowly degrading or it's not that efficient anymore. Like it's like 90% efficient uh, right now from the past 100%. Okay, so it has an effect to our electric. And if the heat energy raises temperature of transmission line conductors or windings of motors, electromagnetism or other electric devices whose function is to work not related to heating, and it is proper to regard it as an energy loss. Okay. So there is now an energy loss if there is too much heating, or if that resistor cannot handle the current that is passing through. Okay. All right. So on the other hand, if the role or if the goal of that circuit is to make the component really, really hot, like for example, the water heaters, the toasters, percolators, flat irons, electric furnaces, etc., that uh, heats anything or something, then that is not an energy loss, because we're taking advantage of the functionality of your resistor, wherein you're heating up something, wherein it has a goal. Okay, so the latter is generally referred to as a power loss if during the period of operation the power is constant. Okay, so that is why, like for example, you're using your flat iron. Okay, if you're not using it and then the power is still constant, wherein you're not really using the heatness of your flat iron, so that is where power loss is now coming from. Okay, or like at really power loss, that is where the uh, you're wasting the electricity that is going to your flat iron. Okay, so you were not able to maximize the electricity that is going through it. All right. So since the power loss is assumed to take place at a current I through a resistor R, it is designated as an I square R loss. So this one came from the formula power, okay, PI squared times R, or briefly I squared times R. Okay, so in other words, this is how we compute or calculate the power loss on a certain circuit. Okay, like for example, that's in a transmission line having a resistance of 0.03 ohm. So take note, our wires also, okay, like your connecting wires, okay, it also creates heat, okay, wherein of course, because it also has a very minimal resistance, let's say 0.03 ohm. So even though this one is super small, it still creates heat. And if it's, or if that wire creates heat, then there is a power loss on that wire or transmission line. Okay, so for example, on that transmission line, we have 150 amps, okay, that is flowing. The power loss will be 150 squared times 0.03, wherein in energy, we've just lost 675 watts. Okay, like we wasn't able to maximize the electricity that is passing through our wire. So that is why we have a lot of we have a lot of kinds of wires. We have copper wires, we have gold wires. So gold wires is really expensive, but a little bit effective, or yeah, a little bit effective than copper. But who will use a gold wire? Okay, it's already gold, so they'll just use it another thing. So aside from copper, there are other wires which I forget the name, wherein they transmit faster and then more efficient than a copper. But they are now much expensive than a copper wire. Okay, so that is why the only thing or the most thing that you will see when it comes to wires or electricity or appliances is always copper, because that is the one that is a lot cheaper than the other wires. Okay. So were you guys able to follow up to this point?
Yes, sir.
Yes, sir.
Did you guys get what I'm trying to explain?
Yes,
Hello?
sir.
Sure? All right, so we're
Yes, sir.
almost done. Okay, we're almost done. So heat energy. So when electric energy is applied to useful heating, such as water heater, it is desirable to know how many gram calories or British thermal units, or in other words, we call it BTU or B2, of heat energy are represented by 1 unit of electrical energy. So in other words, you want to know, okay, the or how long or how strong the power that you need to throw onto that appliances for you to heat up a gram of calories of water, or let's say a gram of water. Wherein we call that 1 gram calories, or in other words, we call that 1 British thermal units. Okay, so precisely performed experiments have shown that 1 watt second of electric energy is 1 joule, and it is equivalent to 0.24 gram calories. So meaning your 1 watt can heat up 0.24 gram calories. So if you want to heat up, let's say 10 gram calories, then you need 10 watts. If you want to heat up 1024, 2400 gram calories, then you need 1000 watts for that. Okay, am I right? 1000, no. 240. Yeah, 240 gram calories. So applying this conversion unit to equation 14, it follows that 0.24 times power times T. So as you guys can see before, we only have watts is equal to power and time. But right now we have heat is equal to 0.24 times power times time. Okay. So again, you can substitute this one by the EI, or voltage times the current, or you can substitute the value of your E into I times R, which now will become I squared times R. Or you can substitute the value of I into V divided by R, or E divided by R, E divided by R, wherein you will get this formula. Okay, so everything was just multiplied by 0.24, because 1 watt is equivalent to 0.24 gram calories. All right. Okay, so just take note that 1 gram calorie is the heat required to raise the temperature of 1 gram of water, okay, or 1 degrees Celsius. Okay, that is 1:1. And 1 BTU is the heat required to raise the temperature of 1 pounds of water 1 degrees Fahrenheit. Okay, so in terms of degrees Celsius, we have this 1 gram. And if we have Fahrenheit, we have pounds. Okay, so yeah, that's it for the Ohm's law. Like, not really, Ohm's law, but series only. No parallel for now. So later on, we'll discuss about the parallel circuits. Okay, so let's just recall the topics that we have discussed. So in this module 1, we've discussed Ohm's law, or electric circuit first, and then the Ohm's law. And what else? So 2 types of circuit. So just a very brief discussion. And then the combination, parallel series and then series parallel. And the electric power. So electric power is almost equal, or equal with energy. And then after energy, we have heat energy. Okay. So yeah, they are all connected with our energy. Okay. Heat energy, electric energy, okay, and just the energy. So any questions so far regarding with the module 1?
Awesome.
So guys,
None, sir.
all right. Okay then. Okay, so actually we still have 6 minutes, but I would like to, I think this is already enough since module 2 is only 10 slides for now. Okay, since I would like you guys to finish the quiz right now, since it's covered the week 1. So you guys cannot, you can take the quiz next week, but it is not under week 1 anymore. So that is why I've rushed your quiz 1, module 1 and module 2. Okay. So the remaining time later on that you're going to have will be your time to finish the quiz. So don't you guys worry. the quiz for the module 1 and 2 is super easy. Okay. So it's for beginner. All right. So let us now proceed to module 2. So we have here series parallel and then parallel series circuits. Actually, all of those are just parallel. Okay. So we have here the circuits combination or combining series and parallel sections with one source of supply are treated in much the same way as simple circuit arrangements. It's just that there is a parallel connection. Okay. And in most series parallel or parallel series circuits, it is generally convenient to consider each series or parallel section as an independent unit. Okay, so if possible, treat them one by one. Okay, you can combine them, okay? Like for example, two resistors, but you still need to treat them one by one as time goes by. Like for example, I've asked you guys to get the individual resistance, individual currents, individual power, individual voltage drop, etc., etc. So using the rules given in the foregoing articles for each one. Okay, so let's have a super simple example. So we have here this circuit wherein, as you guys can see, R1 is parallel with R2, and then R4 is parallel with R5 and parallel with R6. And then the only one that is in series connection is the R3. All right, so the following information is given in connection with the series parallel circuit of figure 3.4a, which is this one. So E is equal to 48 volts, R1 is 6 ohms, R2 is 12, R3 is 3, R4 is 15, R5 is 90, and then R6 is 30. So we have here the questions. Calculate the total equivalent resistance of the entire circuit. So that is one. So you have to add all of those, or you have to know what is the combined value of those resistors. And letter B, the total current of your circuit, and then the voltage drop across each section. So this is one section, this is another section, and then this is another section. So we only have 3 sections, okay? And then the current to each resistor. So current for R1, current for R2, current for R3, R4, R5, and R6. And lastly, the total power taken by the entire circuit. Okay, so yeah, a lot of questions, but they are super easy. Okay, so let's start with letter A first, of course. So the total equivalent resistance of the entire circuit. So as you guys may all know, to compute this one, you have to combine R1 and R2 first, and then R4 and R5 and R6, and then combine the 3 or just add the 3 sections. So first, we have to solve for the R1 and R2 or this section. So to do that one, we have this formula. Okay. So if there is only 2 resistors that is in parallel with each other, like for example R1 and R2, you can use this formula. Okay. R1 times R2 divided by R1 plus R2. But if you have 3 resistors which is in parallel with each other, okay, R4, R5, and R6, you have to use this formula. So 1 divided by 1 over R4 plus 1 over R5 plus 1 over R6. Okay, so this 1 is not limited to 3, so it can have as many parallel connections as you can have. Okay, so up to R7, R8, R9, R10, so on and so forth. But if you only have 2, this one is a lot easier to use. All right, so let's just substitute the value of your R1 and R2. So 6 times 12. So R1 is 6, and then R2 is 12. So 6 times 12 divided by 6 plus 12. So 6 times 12 is around 12, 62, 72.
72.
72 divided by 18, you will get 4. Okay, and then just plus 3. So whatever is the value of R3, just put it right here. And then the same with this one. So just solve this one using your calculator, and then you will get 9. And then voila, you now have the 3 sections. So first section, second section, and the third section. So just add those 3, then you will get 16 ohms as your total resistance. All right. So since we don't have enough time anymore, so we will just continue the rest on the part 2. Okay. So see you guys on part 2.